not moving, we consider the reference frame tied onto this black guy. As it comes in, the velocity of approach is indeed 2b. So once again, now we have 2b over 2b. It's a, homework's up here somewhere, don't. Okay. So again, it's a perfectly elastic collision. This one works too. This one comes swinging in, that one comes swinging out. All these new parallels are just the same. Those come swinging in at some given velocity. Those ones come swinging out at the same velocity. Same deal here. Okay, so now this guy though. So what's our post-collision relative velocity of separation?
V.
0.
0. They're not separate.
So what is velocity? Someone define for me velocity of separation. What does that mean? Relative velocity of separation. So I've got it down here. Relative velocity of separation.
The velocity of the blue one with respect to
What's that?
the velocity of the blue mass with respect to what stuff.
Yes. So velocity of the blue mass with respect to the black mass, or equally direct velocity of the black mass with respect to the blue one. Doesn't matter. That's what relative is. You're comparing the velocity of something compared to something else. So we're not doing it relative to, I don't know, the screen or some other thing. We're doing it relative to each other. So the velocity of separation after the collision is nil. They're not separating at all. They're going along together. There is no velocity of separation. They're not separating. Right? And what's the velocity of approach?
V.
V. That one's pretty clear. So we have 0 over V. So the coefficient of restitution would clearly then be 0, indicating a perfectly inelastic collision. This one, I'm not going to try and do it. This one's perfectly elastic. They do still separate at V, even though it's two-dimensional. Right. So if you think of the red arrow is the velocity of approach, right there, the red guy. And then you can see it's kind of hypotenuse, so there are two velocities afterward.
Did you make these nice little motions?
You might wonder why I chose, or no, I'll restate that. Yes, I did. And I'm not sure why I chose a 5 franc coin for this image. It came over me.
Typically they use zeros now.
I did a little while ago. No, I didn't know. These are gifts, so I took off the internet. No, I don't got that kind of cool gifts. Anyway. Alright, so that's that. So those are just examples of this guy here. So another thing that's common to sort of think about with coefficient restitution, or a nice way to think about it, is a bouncing ball. So if you take whatever, tennis ball, basketball, whatever it is, and you drop it from some height, okay, bounces off the ground, you can assume that the ground basically is stationary. Now in reality, with conservation of momentum, when the ball hits the ground, the whole earth picks up a little bit of speed in that direction. But it's a really small amount. Because the earth really weighs quite a bit compared to basketball. So you pretty much just look at the velocity of basketball. You'll see if you're going to measure relative to the earth, then you're really in good shape. So I guess I'm going to arrange some stuff over here. We've got at least atmospheres. I don't know, where's Joe? I just didn't see him. He was too sleepy. We're going to talk about basketball. Some of the basketball players in the room. Okay. All right. So the relation of C sub r, the coefficient of restitution, to a bouncing ball. So first of all, I just want to define a little symbol. This symbol right here, that means proportional.
Thank you.
Okay? So we'll make proportional. So the height of all bounces is proportional, to b squared. So this is b squared coming up. So the ball is bouncing up off the ground. Its vertical velocity coming up. All right. If you square it, that's proportional to the height. It's not equal. There's a little more to it than that, but it's proportional. All right. So if I were to double the velocity of the ball as it comes back up off the ground, the height would be proportional to b squared. So if I double the velocity, the height is going to be 4 times b squared. If I triple the velocity, compared to my first test, I do multiple tests, right? If I triple it, how high is the ball going to bounce compared to my initial one?
6 times?
We have one correct guess and two not one guess. We have one correct answer, and a couple are not quite right. So if I said it was proportional to the square of the velocity, and we tripled the velocity, so the first case, the velocity is, say, 1, right? So in the first case, so in the first case, let's say the velocity is 1. It's coming up off the ground at 1 unit, whatever, per second, unit per time. Okay? So what's the height going to be? Be 1. And there's some constants in there. But it's going to be proportional to 1. So now if I take the velocity up to 3, now the velocity is now 3. It's not 1 anymore. It's 3. It's going to be proportional to 9. And how did you come up with 9, Jordan? Is that just a brilliant guess, or did you do something?
Yeah, I got my weighted.
Okay. What are you, Dylan? How did you come up with the, yeah, so we're squaring it. So you just square it. Okay? So you take the 3 and you square it. That's all there's to it. So if the velocity was 5 times, what would my height be proportional to?
25.
25. Okay? And so the reason, just to explain why that is, so we have, I mean, what's stopping the ball from just, exiting the atmosphere?
Gravity.
Gravity is stopping it from exiting the atmosphere. Gravity is, relatively speaking, a constant. And if you go far, big enough distances, gravity actually does diminish with how far away the objects are, but kind of distances we're talking about, gravity, consider gravity constant. And so if I have the velocity goes up by 2, how much longer does it take for it to reach the top, come to rest, stop moving upward?
Half?
It's going twice as fast, it's half as long. So now we have V, it comes up at V1. We have, it takes whatever V1 is, it takes 7 seconds. Okay? Now we're going to have to go up at 2 V1. We're going to double the speed. How long is it going to take to come to rest?
3.5.
If it goes up faster, it takes less time to slow down to come to rest. So if I do, okay, that's not very long. Now I do a bigger velocity.
Oh, so about.
Clearly it takes longer. And how are we determining that? How do we figure out that time? Yeah, but how long? That's equation-wise. I have my B, it's straight up. I'm not doing anything clever here. We're going straight in the Y direction. And it's whatever, I don't know, 5, let's see, what am I doing? 10 feet, let's say it's 10 feet per second. I'm tossing it up here, so B naught at 10 feet per second. Yeah, that's true. That's true. So what's T?
Time.
So Jordan said that V equals AT, which is a true statement for this, with our constant acceleration. So I want to know how long it's taking to come to rest. Rest being up top there. It's stopping its motion, momentarily pausing.
V equals 0.
Yeah, but that's not it. V doesn't equal. V is the starting velocity. Okay?
7 feet per second.
But you can also think of it how long it takes to fall. Okay? So starting here, accelerates down, all right, and then goes up with some velocity as it hits my hand again, right? So that's the velocity. Let's talk about it on the way down. With ignoring air friction and stuff, it's the same amount of time you go up and just come down. So if I say that it hits my hand at 10 v equals 10 feet per second, and we say, what's A in this problem? We're doing gravity.
32.
Yeah, I'll call it 32 points. This is one thing in the homework. Some people just say gravity is 32. That is insufficiently accurate. You got to at least do 32.2. 32.17 or whatever, that's fine also. But you got to at least do 32.2. Okay, so 32.2 feet per second squared. So what's T? Anyway, tell me, how do I find T with this? I got one equation. It has three things in it. I know two of them.
You divide it all.
Yeah, so T equals B over A. So it equals 10 feet per second over 32.2 feet per second squared. I didn't have to actually do this one out, so what is it? Okay, so T equals 0.31 seconds. All right? So, back to my thing here. Height of all velocities. So, we can also, this velocity, I said this is the velocity of the thing hitting my hand. It's also, again, ignoring air resistance and so on. It's the same, it's the velocity of it leaving my hand, too. Right, does that make sense? Goes up, 10 feet per second, comes back down, hits my hand at 10 feet per second. Decelerates on the way up and accelerates on the way back down. The same amount of time each time and at the same rate. It's decelerating at 32.2 and then accelerating again at 32.2. So, the overall time it's going up is proportional to the velocity. If I double the time, it's going to spend twice as long going up. If I triple the velocity, it's going to spend 3 times as long going up. I mean, this is a linear relationship right here between time and the velocity. I double that, I double that. Triple that, I triple that. 100 times that, 100 times that. Straight up linear relationship. Okay? Now what's the average speed? As it goes up. What's the average speed?
Total or on
Total. No, just on the way up. Or just on the way down, either way. Whichever way you want to look at it. Yeah. Why? Where'd you get that?
Near the top.
Yes, that's right. So it starts at 0. Either looking at from here or looking at here. The velocity is 0. Right? And then at either end of it, it's v. In this case, 10. And so it's varying linearly. Does that really plan on any of this? All right. So I have t here. I have v here. The velocity, the acceleration is constant. And so if the acceleration is the derivative of the velocity. And so if your derivative of your plot is constant, what does that mean about your plot? What's your plot going to be? The derivative is constant. Straight line. Straight line. So it goes up like that. And the slope here is A. Slope equals A. Which is constant. And so if I want to know the average velocity over some time, up to, I don't know, up to here. This would be, this is my time per second here. This is my 0.31 or whatever it was, 31 seconds here. So what's my average velocity? It's a triangle. So I'm not looking for the area. The area would be the distance covered. Which is the average V. So there's the peak, there's max V at 10, there's minimum V at 0, it's the average.